Last episode, we drew a smooth curve over the real numbers and defined point addition using lines and reflections. Now we take the same equation and move it to a finite field. The smooth curve shatters into a scatter of isolated dots. It looks nothing like the original, but the algebra is identical. The breakthrough insight came in 1985. Neil Koblitz and Victor Miller independently proposed using elliptic curves over finite fields for cryptography. The idea was radical: replace the integers modulo p, used in classical discrete log systems, with the group of points on an elliptic curve over a finite field. The resulting keys are shorter, the security is stronger, and the mathematics is richer. The curve equation is the same short Weierstrass form, y squared equals x cubed plus ax plus b, but now all arithmetic is performed modulo a prime p. Every addition, every multiplication, every squaring happens inside the finite field fp. Consider the SECP 256K1 equation, y squared congruent to x cubed plus 7 modulo 23. We pick 23 because it is small enough to work through by hand. For each x from 0 to 22, compute x cubed plus 7 mod 23 and ask, is the result a perfect square modulo 23? If yes, there are two y values. If the result is 0, there is 1. If not, there are none. Roughly half the values of x yield valid points. The total for this example is 24 points, including the point at infinity. We need a fast way to test whether a number is a square modulo p. Euler's criterion provides the answer. Raise c to the power p minus 1 over 2. If the result is 1, c is a quadratic residue and has a square root. If the result is -1, it does not. Bitcoin's SECP 256K1 prime satisfies p congruent to 3 modulo 4. This special form gives an explicit square root formula. The square root of c is c to the power p plus 1 over 4. No searching required. This is used directly in public key decompression. Given just an x-coordinate and a single bit indicating which square root to take, the full y-coordinate is recovered instantly. How many points does an elliptic curve over fp have? Hasse's theorem gives a tight bound. The number of points n satisfies the inequality. The absolute value of n minus p minus 1 is at most 2 times the square root of p. For Bitcoin's prime, which is roughly 2 to the 256th power, the number of points is approximately 2 to the 256th. The error term, 2 times the square root of p, is only about 2 to the 128th. It is negligible compared to the group size. This enormous group is what makes the discrete logarithm problem intractable. Over the real numbers, y squared equals x cubed plus 7 traces a smooth curve. Over f23, the same equation produces 24 isolated points scattered across a grid. The smooth curve has shattered. There is no visual connection between neighboring points. The geometry that made real curve addition so intuitive, draw a line, find the third intersection, reflect, seems to have vanished. But it has not vanished. The algebra is untouched. The addition formulas from episode 6 carry over exactly. Given 2 points p and q, compute the slope lambda as the difference of the y-coordinates divided by the difference of the x-coordinates, all modulo p. Then x3 equals lambda squared minus x1 minus x2 modulo p, and y3 equals lambda times the quantity x1 minus x3 minus y1 modulo p. Let us compute an example. Take p equals 1, 10 and q equals 4, 5 on the curve y squared congruent to x cubed plus 7 modulo 23. The slope lambda is 5 minus 10 divided by 4 minus 1, which is -5 over 3. The modular inverse of 3 modulo 23 is 8, since 3 times 8 equals 24, which is 1 mod 23. So lambda equals -5 times 8, which is -40, congruent to 6 modulo 23. Now x3 equals 6 squared minus 1 minus 4, which is 31, congruent to 8 modulo 23. And y3 equals 6 times 1 minus 8 minus 10, which is -52, congruent to 17 modulo 23. The result is 8, 17. You can verify. 17 squared is 289, which modulo 23 equals 13. and 8 cubed plus 7 equals 519, which modulo 23 also equals 13. Same formulas. Modular arithmetic. Every arithmetic operation in this finite field must execute in constant time. If a multiplication takes longer when the inputs are larger, an attacker can measure timing differences and extract the private key bit by bit. As Tim Ruffing notes, all field operations, addition, multiplication, inversion, must be implemented so that their execution time is independent of the input values. This is a non-negotiable requirement for any production implementation. Over the real numbers, an elliptic curve is something you can draw and see. Over a small prime like 23, you can at least plot the points on a grid. But over Bitcoin's prime, the group E of FP has roughly 2 to the 256th power points. No human being can visualize or enumerate them, and yet, through pure thought, we know their structure completely: the group order, the generator, the addition law. Steiner called this thinking beyond the senses. The finite field forces us into exactly that mode of understanding. We have the curve over a finite field. We have the group law. Next, the 6 parameters that define SECP 256K1: the specific prime, the specific curve, the specific generator, and the specific group order that Bitcoin chose. Subscribe for Episode 8. The SECP 256K1 parameters. Companion materials for this episode are in the description. See you in Episode 8.